Welcome everyone to this week's data science seminar. I'm the host, David Bader. I'm a distinguished professor at the New Jersey Institute of Technology, and I direct the Institute for Data Science. We're pleased to have with us today Dr. Cynthia Rudin from Duke University. Cynthia is a professor of computer science, electrical and computer engineering, and statistical science at Duke University, and she directs the Prediction Analysis Lab, whose main focus is in interpretable machine learning. She is also an associate director of the Statistical and Applied Mathematical Sciences Institute. Previously, Professor Rudin held positions at MIT, Columbia, and NYU. She's a three-time winner of the Informs Innovative Applications in Analytics Award. She was named one of the top 40 under 40 by Poets and Quants in 2015, and was named by BusinessInsider.com as one of the 12 most impressive professors at MIT in 2015. Wow, that's no easy feat. She's a fellow of the American Statistical Association and also a fellow of the Institute of Mathematical Statistics. She's going to be speaking today on a topic, Stop Explaining Black Box Machine Learning Models for High-Stakes Decisions and Use Interpretable Models instead.
Thanks, David. I'd like us to look at the world as it is now, where we don't use interpretable machine learning models for some really important problems. And what we're using are black box machine learning models. And these are models that are either too complicated to understand or they're proprietary, which means they're somebody's secret sauce and they don't want to tell us what it is. Okay, so what happens when you use these black box models? Well, the first thing is that you could get several years of extra prison time. So this is an example of Glenn Rodriguez. And Glenn was sent to prison at a young age for a crime he committed as a kid, and he was denied parole like 17 years later or whatever it was. And why was that? It's because someone had incorrectly entered some information into a black box predictive model that was being used to predict whether he would commit a crime in the future. And at the parole board hearing, he compared, after the parole board hearing, when his parole got denied, he compared a score sheet to somebody else's, and he noticed an error in his criminal history features. And the model had 137 factors. The score sheet was very long, and so it wasn't that easy to spot an error while the parole board was making their decision. And the same situation probably happens to a lot of people with this same model. If the model was interpretable, it would have been much easier to spot the error. Okay, so what else could happen to you as a result of a black box model? Well, if you lived in California during the wildfires in 2018, you might have been using Google's daily air quality predictions to determine whether it was safe to go outside. And you might have seen Google's predictions that air quality was fine on days when people were also seeing a layer of ash on their cars. So because during the wildfires, Google replaced the EPA's trustworthy air quality index with a proprietary machine learning model from the company Breezometer, which claimed to be more accurate. But clearly this proprietary model was not doing what it was supposed to, and it put a lot of people in danger. Okay, now I've given you just a few things that have gone wrong with using black box models, but there's a tremendous amount more that could go wrong, and probably many things have gone wrong that were hidden, so I don't know about them. And now, people are starting to use machine learning for medical decision-making, for loan decisions, for self-driving cars, and for all manner of things that we really don't want to go wrong. And some people love their black boxes. Some people argue fiercely that they need them. Anyway, so some definitions. An interpretable machine learning model obeys a domain-specific set of constraints that makes its computations easier to understand. So essentially, interpretable models are constrained. They're constrained so that people can understand them better. And I had a more technical definition here, which has a lot of examples. These are examples like encoding knowledge of the domain, or monotonicity, like the model has to increase along one variable, causal constraints, generative constraints, it's constrained, okay? Now there's a spectrum of models that are models on one end that are really very, very sparse, and you can understand exactly how all the variables are jointly related to each other to form the prediction. And then on the other end of the spectrum are these very loosely constrained models that where maybe the model would be forced to decrease along one variable, for instance. Now, I want to give you an example at the first extreme end, where the model is really, really sparse, and you can really understand how everything's working together. And it's an example that's in a very, very high stakes setting, which is to prevent brain damage in critically ill patients. Okay, so say you come into the hospital, you have an aneurysm, it bursts, there's a hemorrhage, blood, this is blood in the patient's brain here. And the patient would go immediately to get scanned, surgery, and then placed in an intensive care unit with continuous EEG monitors to monitor the patient for a potential brain seizure. Now, brain seizures are common. So about 20% of patients that are at risk actually get them. And seizures cause brain damage. In fact, the seizure can actually cause more damage than the actual original hemorrhage. And so doctors do everything they can to try to prevent patients from getting brain damage. They'll shut down parts of the patient's brain using drugs to try to prevent these seizures from damaging the patient's brain. Now, the only way to detect these kind of brain seizures is with continuous EEG monitors, because these are not like seizures where the patient's shaking. This is seizures that are only occurring in the patient's brain. So, so now the thing about this EEG monitors is that they're limited, right? There's not enough people to read the monitors and not enough monitors to go around. And so what ends up happening is the monitors don't get allocated properly. Like they end up staying on people for way too long, and then people who need them don't get them. So allocating these monitors is actually the key to helping prevent brain damage, right? So I've been working with neurologists for many years now, actually. And we designed a model called the 2 helps 2B score that helps predict seizures within 6 hours. Now, the 2 helps 2B score is a machine learning model, but it's small enough that it can fit on a PowerPoint slide. And it's also as powerful as our best black box machine learning models. So I'm just going to put I'm going to put the whole machine learning model on the slide right there. So that's 2 helps 2B. So it's 2 helps 2B because it's 2 HELPS. And then 2 points for the B, so that the doctors can memorize the model just by knowing its name. And then the doctors would, they know what all these things mean. They would check whether the things have occurred, and then add up the score, and the score would translate into a risk using the table on the bottom. So this is a kind of a classic it looks like a classic medical scoring system, but it's actually a machine learning model. And I have to say this because I put this on this slide, and then people go, "Oh, you just made that up." And it's like, no, we didn't. This is actually, it wasn't created by doctors. It's actually a machine learning model. It's just as accurate as black box models for this data set. The data set has 70 variables. The model chose which 6 variables to pick for it. The algorithm chose how many points to assign as well. It doesn't force you to trust it. It's not like a black box where you have to go, I trust it or I don't trust it. Here, the doctors can look at the model and decide whether or not they want to trust it. Doctors can also calibrate the score with information on the database. Like if the doctor looks at the patient and says, that patient has this thing, that thing maybe is worth about a point. So I can add that in. So as I mentioned, the data set that we use to create the model is actually quite large. It has over 70 variables. And the variables chosen for 2 helps 2B were chosen by the algorithm. So I want to, I have, I think, only one slide of math, but I want to show you just the formulation for the algorithm that produced the 2 helps 2B score. And the algorithm is called RISC-SLIM, or risk-calibrated supersparse linear integer models. And it has 2 terms in it. There is a logistic loss term, which is the same term as in logistic regression, and it just keeps the model accurate and risk calibrated. And then there's a sparsity term, which says try to put as few non-zero, components into the model. Like try to keep the model really, really sparse. And then the constraint here says that all the coefficients have to be integers between -10 and 10. So that's why the 2 helps 2B score had like 1, 1, 1, 1, 1, 1, and 2. Like those numbers, they could have been any number between -10 and 10, but the algorithm chose all those ones and then a 2. But it could have, like I said, it could have chosen anything between -10 and 10. Okay, now, if you are an optimization expert, you would immediately look at this and say, this is a really hard problem. This is actually a mixed integer nonlinear program. And the feasible region of this optimization problem is the integer lattice. So you would say, look, even if you put that into a generic mathematical programming solver, it would take years to solve this problem, even for a reasonably small size data set. But my point is that this problem, this is a math problem. We think that this problem should be a problem of computer scientists and mathematicians, statisticians, not doctors, okay? This is the problem we claim doctors want to solve if they could, but in fact, this is a problem that should be our problem and not their problem. And so we've designed our own tools to solve this problem. Specifically, RiskSlim is a cutting plane algorithm that incorporates elements of branch and bound. But so now, when the patient comes in with their, aneurysm that has burst, the doctor reads the EEG monitor and says, "Oh, this patient has this, this, and that. They have a 2 helps 2B score of 3. I'm gonna, label them high risk and place them on monitors for at least 72 hours and start them on preventative medication so they won't get a seizure." Now, so far, the 2 helps 2B score was validated in a study that I wasn't a part of. So the doctors actually took the model and used data from different hospitals that the model was trained on, and then validated it on this extra cohort. And they found that it validated really well, and it's been implemented in several hospitals. They also did a study in 2018 that they showed it resulted in a huge reduction in the duration of EEG monitoring, which allowed them to monitor a huge number more patients than before. So 2.82 times the number of patients than before. And the doctors were really proud of this number because it means that it's reducing the amount of brain damage, it's reducing the amount of death. It's also saving a little bit of money, but the main point is this 2.82. That's the number that the doctors are really proud of. Okay, so that's how interpretable models are supposed to work, but don't they lose accuracy because they're constrained, right? When you constrain something, you think that you sacrifice accuracy. Well, I want to go back to this example that I started with, where Glenn Rodriguez was denied parole because his COMPAS score was miscalculated. Now, COMPAS is very widely used across the justice system, and it's proprietary. And you'd think that a black box model or a proprietary model that's been designed by a company would be more accurate than a very simple model, but that's not always the case. And in fact, it's not even usually the case. So we did an experiment where we compared the accuracy of COMPAS, which is, again, proprietary. We compared that to the accuracy of our machine learning method that we were working on at the time, called Corals. We've since advanced beyond Corals, but Corals was the latest machine learning method we had when this data set came out. This is a data set from Florida. And so we took the Florida data, we built a machine learning model, and we compared the accuracy of it to COMPAS. Okay, so I want to show you what happened when we applied Corals to this Florida data set. So we came up with a machine learning model that was so tiny that it fits in the corner of a PowerPoint slide. And again, this is not a rule of thumb, it's actually a machine learning model. And the model looks like this. It says if the person is young, like if they're 19 to 20 years old and they're male, predict arrest within 2 years of their COMPAS score calculation. Also, if they're a little bit older, right, 21 to 22 years old, and they have 2 to 3 prior offenses, predict arrest within 2 years, again, of their COMPAS score calculation. Also, if they have more than 3 priors, predict arrest, otherwise predict no arrest. And we looked at this model and we thought, there is no way this model can be as accurate as this proprietary model that they're selling. No way. But we were wrong. So this is tenfold cross-validation. So this is the data set divided up into pieces, right? 9 folds train, 10th is test. It's different, each different color is a different fold. And corals produced essentially the same model across folds, and it looks like that. And so as you can see, they're about equally accurate. And not only that, it didn't really matter which machine learning method we used. They all performed about the same. And some of these were like really, black box, like boosted decision trees, which is a huge model, support vector machines with radial basis function kernels, random forests, and then Compass, which is proprietary. And they're all about equally accurate to that model over here. Okay. So, there was a huge debate a couple of years ago about the algorithmic fairness properties of Compass. But the truth is that we just don't seem to need Compass at all. So, why are we still using it in the justice system? And that's not clear to me at all. Okay, so far, I just talked about interpretable machine learning and how it doesn't lose accuracy. I want to contrast that with explainable machine learning. So explainable is where you start with a black box and you explain it. So it's like a post hoc explanation process. So you start with a black box and you do something to it to explain it. You either create another model to approximate the black box, or you compute derivatives of the black box, or you visualize what part of the input the model is paying attention to. You make some excuse for why it's okay to use the black box rather than replace it with a model that's inherently interpretable. Now, I want to point out that these two things are actually incredibly different in practice. They have very, very different implications, like a chasm between them. So first of all, I don't think explanations of black box models can be used in practice. And there are some really good reasons for high stakes decisions. So the first reason is double trouble. So double trouble is where it forces you to rely on two models instead of one. You have the black box and the explanation. You have to rely on both of those. And those models have to disagree with each other, because if they didn't, you could simply throw out the black box and just use the explanation as an inherently interpretable model. So these two things have to disagree with each other. But then the question becomes how often they differ from each other. Now, a lot of people, they come up and they say, oh, my explanation is right 90% of the time. And I say, but that means your explanation is wrong 10% of the time. And if I can't trust your explanation 10% of the time, I can't trust your model 10% of the time. And so then what are you doing, right, at that point? That you can't trust either one of them and you have to troubleshoot both of them. Now, typographical errors are a problem that doesn't go away when you explain black box models. So just like I showed you with the Glenn Rodriguez case, Compass, even if you explained it to its forever and explained which variables were important, it's not going to stop the problem of typographical errors because you have 137 input variables. And then also, if you can produce an accurate interpretable model, why are we explaining black boxes? It doesn't make any sense, right? I'm not saying we should use the corals model, right? I'm definitely not saying that's like ready for like the criminal justice system, but why in the world are we using Compass? I have no idea. So you have this other issue with black box models, which is that when you explain them, you can get confused. And actually, the explanation can really cause a scandal. So explanations are not actually explanations of what the model's doing, right? Approximations are not explanations, and they could get variable importance wrong and cause a scandal. It would be terrible if that happened, right? Okay, so let's say you have your black box, which is this model right here. And then let's say that you tried to explain it by producing an approximation that's, fairly similar to the black box. But they can depend on different variables, you see? So it's possible that the black box depends on maybe age and number of prior crimes, whereas the approximation depends on age, priors, and race. And then you might actually end up thinking that the black box depends on race because the explanation depends on race. And, you could say this is stupid and it would never happen, but it actually might happen. And it actually did happen. And it happened with Compass. Okay, so somebody tried to explain Compass. They created an approximation. The approximation depended on race. And then they claimed Compass depended on race. And this actually is what happened with the very famous ProPublica article that maybe a lot of you know about. So the article, the nice thing about this article is that they actually provided compass scores so that you could, they provided outputs of the black box model, and they provided all of their analysis, so you could see exactly where they went wrong. Okay, so and this is exactly what they did. They took compass, they approximated it with a linear model, and then the linear model depended on race, and then they wrote this whole article saying that compass depends on race. Okay, so let me just give you a little bit more details about what happened here. So ProPublica showed that the false positive rate and false negative rate of compass varied by race. And then they suggested, ProPublica suggested that this might not be a good comparison. We should condition on age and number of priors and re-examine. So in other words, they were saying, well, maybe all of the difference between false positive and false negative rate, that all maybe arose because the distributions of people and the different races of people in the database are different, right? There's the ages were different between blacks and whites, and the number of priors was different. So maybe we should just look at condition on age and number of priors and re-examine. So they did that, but they still found a linear approximation to compass with a low p-value for the race covariate, which basically says that race is important. And so they concluded that compass depends on race. The problem with this analysis, of course, is that we don't think compass is linear. And so the conclusion actually doesn't follow from the assumption, it doesn't follow from their analysis. So I want to just show you a little bit more detail about what happened here. Okay, so we're going to grab this data set from Broward County, Florida, and try to see what's actually inside compass, trying to see what compass is actually doing. Okay, so the best way for me to show you what we think compass is doing is to plot something for you, is to plot the data. So this is a scatter plot of the compass scores as a function of age. Okay, so age is the key to all of this. And I hope you can see this, but there's a fairly sharp cutoff for compass scores at each age. I mean, there's a few outliers, but there's a lot of people who are right on that boundary right there, tracing at that lower curve. And I think that these are possibly the minimum compass scores for each age. So, I mean, these few outliers could arise from, say, typos within the database, but overall, not pointing to a linear function of age. And it looks like compass depends very heavily on age, especially for younger ages. So we thought, clearly ProPublica's analysis is not correct, because their linear approximation is just there's no way that follows. So we decided that we would try to then figure out the answer to the question they wanted to answer, which is, does compass depend on race in addition to age and criminal history? So we took out this lower curve, we subtracted that out, okay? And then we tried to examine whether the remainder depended on race, and it really didn't seem to. In fact, we ran machine learning models with and without race to see if they need race to predict compass well, and they performed similarly. They weren't relying on the race variable to gain predictions. So in any case, what we think happened here is that ProPublica used the they knew that there was a correlation between race and age and race and criminal history, right? Those are correlated because of systemic racism in society, but they didn't take into account the way those correlations happened, and so their conclusion wasn't correct. Okay, so then it makes you kind of wonder, how did they find all these examples, right? They had a whole bunch of examples in their paper of a Black person and a white person, where the Black person has a much larger criminal history and a lower compass risk than the Black person. So it's like, well, how is that possible? But if you look at these two people, I mean, I think the example would be much. Look, the Black person is much, much younger than the white person. Okay, so if compass depends heavily on age, that could explain how this happened, right? Vernon Prater, he's old, so he doesn't get the age points. And I'm not saying I agree with this. I'm not saying this is right or ethically okay. But if ProPublica had compared two people of the same age, it would be much more convincing that COMPAS depended on race in addition to the strong dependence on age. And so, how is it possible? How do we explain how they found all of these pairs? So they found so many pairs where you see this uneven criminal history and COMPAS scores that don't seem to make any sense. But I think the real problem is actually something different. I think the real problem is inherently a lack of transparency. And in particular, if you have a COMPAS survey, which is 137 factors entered by hand, then even a 1% error rate in entering that data into the system leads to a 75% chance of at least one typographical error on a survey. And so this is just a serious disadvantage to complicated or proprietary models. This affects everybody who's entering the criminal justice system at all. It's a systemic source of unfairness, which is exactly where it brings me back to the very beginning of the talk with Glenn Rodriguez. So we were curious about how often this particular issue happens in Florida, because we had the data from Florida. How often do we see these kind of weird typographical errors maybe causing problems with the COMPAS score? And the answer is all the time. So here's a table of just some individuals, and this is their COMPAS. They all have COMPAS violence score of 1. So in other words, these people all have the lowest possible COMPAS violence score. And yet, if you look at their criminal history, it's pretty intense. Some of these people have like very, very scary criminal histories. And so it's really shocking that they have the lowest possible COMPAS violence score. And now I'm showing you only like the tip of the iceberg here, like that there's more people on this list. So here are people who have scores of 2 and 3. So again, low COMPAS violence scores, but large numbers of prior offenses. By the way, this is the number of prior charges. This is the number of prior arrests. So these people are, yeah. Anyway, so typos are a real disadvantage of explained black boxes over interpretable models. Typos are much easier to spot if the model is not complicated. Now, while we were doing this, we even found possible typographical errors in the COMPAS documentation from the company that makes the model. So we even questioned that in our paper, and we think actually that the correct notation should have been like this: that there's a nonlinear transformation of age. And in fact, North Point, the company that makes COMPAS, they actually responded to our article, and they essentially admitted to the fact that there was probably a transformation of age. So they admitted we were correct. Okay, so anyway, back to interpretability versus explainability. I want to bring up a picture from the DARPA Explainable AI BAA. So this is a DARPA program on explainable machine learning. And they had this plot that I looked at this and I felt very uncomfortable with it. And so let me tell you why. So first of all, there's no quantification on these axes. This plot doesn't arise from any real problem. It's just mathyism, right? So it's like Trump with a Sharpie, it's like somebody drew it, right? Trying to show that you have to sacrifice explanation effectiveness for good learning performance. That's what it's supposed to show. And I thought, well, there's, this not only is the figure fake, but it's supposed to illustrate something that doesn't exist. So it's or that doesn't make any sense to illustrate. So they seem to be like showing what would happen if you ran a bunch of different machine learning algorithms on a static data set. But that's not the way we do data science. We don't have a static data set. We don't use a fixed evaluation metric. When we do real data science, we're supposed to run our, whatever algorithm we're running, and then look at the result and use the information we get from the result, the interpretation of it, to go back and fix whatever problems we found in the data and whatever problems we found in our evaluation metric. And when we do that, the level of understanding that we have in the problem helps us achieve better accuracy the next time around. So the whole plot, the whole setup of this is completely misleading. And then even if you did use the static data set, with a fixed evaluation metric, the trade-off doesn't actually look like that. The trade-off looks more like what I showed you with the COMPAS scores. You try a bunch of different machine learning methods and they all perform the same. It depends on your data representation though. Like things get more interesting when you have computer vision problems where you need to use neural networks. But even in those cases, we can still get good interpretable models that are the same accuracy as our black box models. And I'll talk more about that in a little bit. So the trade-off doesn't happen like this in practice. It's more flat. And then also they didn't even talk about whether they were whether the plot applies to explaining black boxes or designing inherently interpretable models. And as it turned out, it was just about explaining black boxes. It wasn't talking about inherently interpretable models at all. So after a few years of sort of listening to people talk about their great explanations for black box models, I finally, got off my chair and wrote a paper that just try to explain this to people that you really shouldn't do this. You really should stop making excuses for these black box models and really just try to make an effort to design models that are inherently interpretable, especially for high stakes decisions. And the paper had please in the title earlier, and they made me take out the please. And so like the editor maybe take it out. So it sounds more commanding, like stop doing this instead of please stop doing this. Anyway, I gave a lot of reasons, and I'll tell you some of them, which are exactly all the reasons that I just told you. Typographical errors cause problems for black box models, whether or not you have explained them. Black box models still force you to trust the data set, even if you explain them. I don't know a large data set at all that is trustworthy. The issue with double trouble, where it forces you to rely on two models instead of one, and those models have to disagree with each other. Otherwise, you can throw out the black box and just use the explanation. And also the explanations are not really explanations. They don't use the same variables. And the key example for this is the Propublica Scandal, where they said that COMPAS depends on age, criminal history, and race, but their analysis is wrong. It possibly only depends on race through age and criminal history. Of course, you'll never really know that unless you actually can see into the black box. And then finally, if you can produce an interpretable model, why should you explain a black box? Do you really want to extend the authority of the black box? Why don't you just replace it? Now, as I mentioned, there is a bit more subtlety to all of this, because there are really two different types of problems, machine learning problems. And those are problems that involve tabular data versus raw data. So tabular data those are the kind of problems I always end up getting. I don't know why, but the problems I tend to work on are problems where you have a set of variables and you have meaningful, all the variables are meaningful and you get values for them, right? These are problems that occur in healthcare and criminal justice and the social sciences. I did a lot of work in energy grid reliability in New York City, so I get problems like this, okay? So that's tabular data. And I already showed you some results with tabular data. Whereas if you're working with raw data, that's kind of like computer vision problems or time series data or large text, large amounts of text. Pixel really isn't a meaningful predictor of what's in the image, right? Nor is a bit of a sound wave or a word in a text. So for those problems, you really need a neural network. But like I said, in the case of raw data, the definition of interpretability needs to change, right? Nobody would ever say that a model that's sparse on pixel space is actually interpretable. That makes no sense. Whereas with tabular data, sparse models are actually often very valuable. So you have to define the definition of interpretability carefully. And then, so you're probably wondering, so maybe for tabular data, you're finally starting to believe me that you don't lose accuracy with, tabular data after I showed you some of these examples. But even for the raw data, the answer seems to be no, they don't really lose accuracy, but you have to be able to choose a good definition of interpretability. But in most cases, interpretability actually helps accuracy because you know what you're doing. And then again, you can refine your problem. So we were wondering what it actually means to define an interpretable deep neural network for computer vision. And we have a couple of papers on this now. So we actually, have made a real effort to try to figure out what this means. But I had to do it because I was sick of the computer vision people telling me that it's impossible to have an interpretable deep neural network. So I figured that we could try to do some things. And we started out with case-based reasoning, but right now we're working on something a little different, which is neural disentanglement. So this is a paper that that I'm just going to tell you briefly what it does. It's called concept whitening, and the idea is to disentangle parts of the latent space, as I'll show you. And this is kind of like doing PCA for like principal component analysis for neural networks. All right, so convolutional neural networks they're not naturally disentangled. You do not have all the information about airplanes going through one node, all the information going about cars through another node, all the information about dogs going through a third node. That is not the way neural networks typically work. Usually the information is entangled so that anything, all information about airplanes, it goes through lots of different nodes, okay? And so what people have been trying to do to explain neural networks, so explain black box neural networks, is that they might create what are called concept vectors. So let's say that you have a bunch of images, you feed them through the network, and then for a concept, maybe concept one is like airplanes, and then you look to see which neurons are being activated. So here, neuron 1 and neuron 2 are both somewhat activated whenever there's an airplane image that appears. And then maybe concept 2 might be trucks, and so neuron 1 and neuron 2 both activate very highly when there's a truck, okay? So to try to understand this latent space, people will create these vectors toward the concepts. But this doesn't really work. And there's good reasons why it doesn't work. I mean, first of all, the concepts aren't necessarily located in a small part of space, but also sometimes the concept vectors for totally different concepts are pointing in the same direction. So you can have like I think we found a case where a concept vector for a bridge, like a bridge going over water, was the same as like a concept vector for something that had nothing to do with bridges. It was like totally, totally different thing. I can't remember what it was. But yeah, so looking at the network post hoc really doesn't make you understand how the concepts are set up in latent space. What we'd really like is to actually have the concepts along the axes of the latent space so that it's disentangled. So we designed this technique that would replace the batch normalization layer of a neural network with this new concept whitening layer. And then when the concept whitening module is added to a convolutional neural network, the latent space is whitened. Whitened means decorrelated and normalized, like white noise. And the axes of the latent space are aligned with the concepts of interest. So for here, it would actually try to create that latent space so that it's decorrelated and normalized, and then it would align the axes so that all the airplanes were on this axis and all the cars were on this axis. So whenever an airplane showed up, the only information that the network would record about airplanes, or what it thought was an airplane, would go through neuron 1. And same thing with trucks and neuron 2. Okay, so when CW is added to different layers, it does something really cool. Like when you add it to the very early layers, remember, all the information about airplane has to go through one neuron. And so if you look at what's highly activated on that one neuron, that tells you about what the network, what information the network is using about airplane to in its final classification. So if you add the CW to the second layer, the network doesn't have time to figure out what an airplane is. It's only 2 layers in. And so it just comes up with something that it thinks is, it's the relevant information about airplane it wants to use for solving the problem. And as you'll notice, none of these are actually airplane. They're basically blue background with some darker silver object or white object in the middle. which is really interesting because, you know, that's like an abstract notion of an airplane that you could imagine the network would construct in the second layer. And then for the concept bed, it seemed to want to use warm colors. And for person, it seemed to really like busy textures. So in earlier layers, right, the color and texture information related to the concepts seem to be represented along the axes when it's, you know, it's trying to represent airplane, but, you know, or it's trying to represent what information it needs about airplane to do its final classification. And so it ends up with, yeah, it's kind of cool stuff. And then of course, when you add CW to the later layers, it actually does align the axes with things that look very, very much like the concepts. Airplanes, beds, people, that's what we asked it to do. So we can see how an image travels through the layers by looking at the airplane axis and the bed axis of an image, right? This is just two concepts that we just chose. So we chose this interesting picture here because, first of all, it has neither a bed nor an airplane, but it has a sky and it has warm colors. So it seems like it ought to be, you know, relevant to some of these earlier layers, right? So in earlier layers, the network is highly activated on the bed neuron because it's got that nice warm color to it. But then as the layers increase, it starts to realize, hey, you know, this might not be a bed. And then it thinks, oh, wait, maybe it's an airplane. It's got some blue sky in it. And then, yeah, it's still doing that. It's kind of like a, you know, you wonder where it's going to go. And it's like, I know about that airplane. Maybe it's a bed again. Yeah, no, it's really an airplane this time. And then, yeah, so finally at the end, it's figured out that, hey, it's definitely not a bed. Might be an airplane, not a bed. Yeah. Okay, cool. So the advantages of CW over just the regular batch norm is that, you know, there's no sacrifice in accuracy. The accuracy is just on par with the standard CNN baseline that you start with. So you start with the black box, replace the batch norm with the CW, and you get the same accuracy. You just have to run for one additional epoch. It's really easy to use. You just you start with your black box model pre-trained. You do the replacement, train one additional epoch, which means just one pass through your data set. But it does, you know, it does require some extra work because you need to construct the data sets, the training data for the concepts. You need to have airplanes and cars and tell it, okay, please align the axes with the airplanes and the cars. So it does require that extra data. But it disentangles the latent space. So like I said, it's like principal component analysis for neural networks. All right. So just to summarize what I've been talking about, predictive models are everywhere. They're being used for lots and lots of high stakes decisions. Don't we want to be able to troubleshoot them? Don't we want to be able to detect if they're biased in a harmful way? Don't we want to be able to ensure that a typo didn't make a decision for us? We don't want our criminal justice system to be making decisions based on typographical errors. That's not the way it's supposed to work. Don't we want to be able to, you know, use these models in high stakes decisions, like I showed with the 2 helps 2B score? Don't we want to be able to understand these models? And if so, we should design models that are inherently interpretable. Thank you.
Thank you, Cynthia. Excellent presentation. And for those who are on the Zoom, you can ask questions either by typing in the chat or if you'd like to unmute and ask a question. Maybe I'll read the first question that comes from, I believe, Gilles Gnordja, and apologies for mangling the name. Regarding the first use case on the brain, what's the relation between the objective function and the score?
Oh, it's the same as in logistic regression. It's a logistic transformation. It's like, yeah, it's just a logistic transformation. So you take the score and you would do 1 over 1 plus e to the negative score.
Thank you. Are there any other questions? Please use the chat. Maybe I can ask one. And you gave the example of compass you used for determining recidivism for courtrooms. And this is such a remarkable case. How would the public know, or what do you think the right of the public is to know when such models are being used? And how do you explain this to the public so that they're more informed about being able to weigh into such uses of machine learning?
Oh, that's a good question. So I don't know about the public so much as the courts. So there have been lawsuits. There was a lawsuit specifically about Compass, where someone claimed that the use of a proprietary model to make a decision actually violated their oh shoot, what's the name of this law? You're supposed to know what evidence is being, how your decision's being made, essentially. And the courts upheld the use of the proprietary model. So so far the courts have said, no, we want to encourage the development of such models, and therefore we're going to allow the use of them. So the thing is, though, I think things should change. I think there should be at least some effort from on the legal side to force models that are being used in high stakes decisions to, if they're going to be proprietary, they should have to prove that there's no interpretable model with the same level of accuracy for a high stakes decision. So something like credit risk or recidivism prediction. I think they should have to prove that there's no interpretable model with the same level of accuracy. Because you see, if that's true, then we'll never have black box models for high stakes decisions, as far as I can tell. If that makes sense. Credit scoring models have been used forever and they're all proprietary. Like sometimes you get really misleading, weird explanations for why your credit score went up or down. Like I paid off a mortgage and my credit score went down because it's like you have fewer accounts now, so your credit score went down. It's like, that means your credit scoring model is not very good because I should be more trustworthy, right? Because now I've paid off my loan. But yeah, so I think the reason these models get to be proprietary is because they're selling it. You know what I mean? There's like a whole market for them. But the problem is the people who are subject to them are not the people who are designing them. So yeah, it's really problematic.
So Mike Merrill made a comment that he'd be more worried about explaining the output of a model to a lawyer than the public, I assume. And there's a comment from Neil Petrov. So it would seem that bad data negatively impacts black boxes as well as more interpretable systems. Can you talk more about how the latter would more easily show the use of bad data, for instance, the typos in coding of the records that you mentioned?
Well, like for the Compass cases, then, if there was a typographical error, like, if there were like let's say there were 4 or 5 inputs to the model, then the person would be like, wait, I got a high Compass score? How did I get a high Compass score? All of my scores should have been 0. I haven't committed a crime since I was a kid. And the judge would be like, oh, wait, let me just go check those 5 numbers. Oh yeah, you're right. Okay, I'll just fix that for you. You see what I mean? It's just much easier to correct things when there's not that many of them to correct. And when they're not hidden behind some smoke screen, a 137 question survey that somebody filled out 2 days ago or whatever. I think it's pretty clear that it's much easier to troubleshoot much smaller models.
Right, your models were interesting in that your interpretable models were very, very small, very easy to put up on a slide. Do you think all of the interpretable models will be as elegant as the 2 that you showed?
For criminal recidivism prediction, yeah, I do. And I'm saying that after having written multiple papers on this particular topic, and I've gotten data from all over the place. I've gotten, data from multiple states, and yeah, working in Scrum for years, I can tell you that for that problem, yeah.
Humans may be easy to predict in behavior.
It's not that it's easy to predict the behavior. It's just that you can't get any better accuracy with a black box model. It's actually really difficult to predict the behavior, but you're not going to be able to predict. It's actually really difficult to figure out whether someone's going to commit a crime, right? Because there's a lot of things that could happen to them in those 2 years, right? Whether they get a job, whether they don't, whether they have family support, whether they don't. You can't predict that stuff, but you're not going to get any better with a neural network in predicting that. It's not going to help.
Got it. So Bill Bishop asks, he says, really interesting presentation on several levels. Besides the desire to preserve intellectual property, what arguments are advanced in favor of the black box?
Well, yeah, so intellectual property is a big one. That's a big one. But also people love the idea that a black box holds some secret to it, and that you can't, that if you understand the model, you're going to miss the secret. There's some like very subtle thing in there that you're going to miss, and I've had people literally come up to me after I give a talk and start screaming at me, like yelling, like, right, like yelling at me, like, no, you're never going to get the accuracy of black box with an interpretable model. And I'm like, I've worked on like a million different applications. I've always been doing applied machine learning for my whole career. And, I just haven't seen a case where we really need a black box. I'm sorry, and now I'm working in computer vision. I'm working in material science, all kinds of medical applications. So you can tell me that, you can tell me your experience, and that's fine. But, my experience is pretty, it's pretty broad at this point that I can say that, that I feel confident saying that.
Bill asked a follow-up question. Are you aware of any field that forbids black box models, for instance, because of safety or transparency?
Yeah, so a lot of healthcare, so it's really hard to get a black box machine learning model through into use in healthcare, unless it's not high stakes. It's very hard to get that to happen. So there's very few. The model that I just showed you is one of very few models that are actually used in practice that are machine learning, really full-blown machine learning models.
Joshua Pearl has a question.
First of all, I like the idea of fighting black boxes because I always think that somebody is hiding something. Specifically, your examples were more like with images. We were using machine learning to predict who is the parent concept of a new concept added to a terminology. Did you try anything in this direction of a concept in a terminology?
Sorry, a concept in a terminology? What does that mean?
Like ontology, if this is more familiar, like a knowledge base of concept.
Oh,
and you have to, like SNOMED, you have to add new concept to SNOMED. We were trying to do it with machine learning to find out who are the parents to whom we connect the new concept. I wonder if you have any experience with something like concepts in your experiments.
Okay, so there is a body of work that does that, and I think it's fantastic. I haven't worked in that for high stakes decisions. I have used those kind of ontologies to help with. We wrote a paper recently on playing a game, a word game, but that's not high stakes at all. But yeah, I know exactly what you're talking about, and that stuff does definitely fall into interpretable machine learning. Yeah.
You believe that it's possible to use interpretable machine learning for such problems?
Yeah, that definitely. So using an ontology and trying to embed it into them and using its knowledge to embed that into the model, that is definitely interpretable machine learning.
Hey, this is interesting. Thank you.
So we have time maybe for 2 more questions. One comes from Stephen Howell, who asks, some models are certainly more or less interpretable than others. How do you draw a line between sufficiently interpretable models, and would you propose generally avoiding a few models, preferring to use a few models or something different?
Yeah, so that's a good question, because the definition of interpretability has to depend on the domain. So again, computer vision versus the 2 helps 2B score rate versus tabular, sparse tabular. Oh, let's try that again. Okay, yeah. So so computer vision versus like tabular data, the definition of interpretability is very, very different. And so you have to get a domain expert to tell you what definition of interpretability is the right one for that domain, or you have to refine it with experts. So right now, like I said, I'm working with radiologists who are working on mammography. And what does it mean to be interpretable for computer-aided mammography? So we're trying to define that, and there's probably many ways you can define it, but we need at least one that'll help that actually will help the doctor to make the decision. For a lot of medical problems, scoring systems have been in use for 100 years. So we're trying to design scoring systems because they resemble what doctors have been using. And so it's a language they would use before machine learning even existed. Like without machine learning, they'd be designing scoring systems. And so that's why we chose that one, because it has a historical foundation to it.
Thank you. And there's a couple questions about CW that you mentioned, and I'll just sort of combine them. One from Hive Fan asked about how sensitive or robust CW is, and another question asked about if CW has a minimal impact on neural net accuracy, and does that include false positive, false negative, etc.
So we haven't done huge amounts of experiments on CW. We just published it at the end of 2020, so it's kind of new. So I'm not sure about the answer to that, but that's definitely something that could be investigated. And if it doesn't, if for some reason it's messing up some property of accuracy, we could definitely consider ways to improve it. But yeah, that's a good question.
So Cynthia, thank you again for such a wonderful talk and discussion. It's such an intriguing topic, and it was great to hear this from you. And I want to thank all of the audience here on Zoom and on YouTube again for attending. And again, Cynthia, thank you so much for this just absolutely incredible lecture.
Thank you. Great questions too.